Welcome to The Explainer. Today, we're not just looking at calculus as a bunch of boring rules in a textbook. No, we are looking at it as the literal physics engine that codes our reality. Think about our 3D world almost like a massive video game. Calculus? Well, that's the background code running constantly to figure out exactly where things are, how fast they're moving, and how they all interact. Okay, let's dive into this. Picture this scenario. It's pitch black outside, and a car drives right past a tall street lamp. As the car moves away, its shadow naturally stretches out way in front of it. So here's our hook for today. If you know the exact speed the car is driving, can you figure out the exact speed the tip of its shadow is shooting across the pavement? It honestly sounds like magic, but calculus gives us the exact formula to crack this code. So here is our roadmap for the explainer. First up, math in motion. Second, we're tackling related rates. And finally, optimization, where we'll design the perfect box. Let's get to it. Module 1, Math in Motion. We'll be focusing on velocity and acceleration. Now, to build our physics engine, the very first thing we have to do is separate speed from velocity. In everyday conversation, sure, we use them totally interchangeably. But in the realm of physics and calculus, they are entirely different beasts. Speed is just the magnitude. It basically tells you how fast an object is going, and it's always going to be a positive number or 0 if you're stopped dead. Velocity, though, gives you the magnitude and the direction. It tells you if the object is moving to the right or the left, up or down, simply by being a positive or a negative number. So, if you take the first derivative of our position, boom, that gives us velocity, our direction. It mathematically dictates whether we're moving forward or backward. But what happens if you take the derivative again? That second derivative gives you acceleration, and acceleration acts exactly like reality's accelerator or brake pedal. A positive acceleration might push you to the right, but say you're walking left and a massive gust of wind hits you from the right, that negative acceleration acts as a brake, actively slowing down your velocity. All right, moving right along to section 2, tackling related rates, where we'll look at sinking water and moving shadows. Now, every single source I looked at, from intense MIT lectures to online tutorials, uses this exact same 4-step cheat sheet to solve these related rate puzzles. It's such a brilliant framework. Step 1, draw a picture and label your known and unknown variables. Step 2, figure out an equation that relates all these quantities together without any derivatives yet. Step 3, differentiate both sides implicitly with respect to time using the chain rule. And finally, step 4, just plug in your known numbers and solve for that unknown rate. Okay, imagine a massive inverted conical water tank, basically an upside-down cone. Now, water is draining out of the bottom at a constant, steady rate of 2 cubic feet per minute. What we really want to know is exactly how fast the water level, the height, is dropping at the precise split second the water is exactly 5 feet deep. To solve this real-world puzzle, we need an equation that connects the volume, the radius, and the height. And here is the coolest geometric cheat code I discovered for dealing with way too many variables. The standard volume formula for a cone has both a radius and a height, but hey, we only care about the height. Well, if you imagine a flat 2D cross-section of that tank, it basically forms a triangle. Because the water sitting inside forms a smaller, geometrically similar triangle, the ratio of the radius to the height never actually changes. It's locked in. So if the tank has a radius of 4 and a height of 10, then the ratio of our water's radius to its height is literally always 4/10. So by substituting that 4/10 ratio right into our formula, we can completely eliminate the radius before we even take the derivative. It's awesome. Now we're left with this beautifully simple static equation relating only the volume and the height. And then the absolute magic happens in step 3. We hit that equation with a time derivative, or DDT. Because things in our real world are actually in motion, taking the derivative with respect to time literally sets the math in motion. It changes a static volume into a dynamic rate of draining water. Then you just plug in your knowns and solve. All right, let's bring this all back to that shadow hook from the beginning. Imagine a 30-foot street lamp on the left. 10 feet away is the base of a falling object, and we'll call its height y as a function of time. The light rays pass right over the top of the object, casting this long, moving shadow on the ground. We want to find the exact speed of that shadow's tip, which we'll call x as a function of time. Just like with the water tank, the secret sauce here is similar triangles. We've got a massive triangle formed by the 30-foot lamp and the entire horizontal distance to the tip of the shadow, x. And nested right inside it, there's a smaller right triangle formed by the object y and its distance to the shadow tip, which is x minus 10. By setting up a ratio between the small triangle's height and base to the large triangle's height and base, we literally connect the vertical drop directly to the horizontal speed along the pavement. It is a perfect translation of a physical situation right into a differential equation. Which brings us to our final section, optimization, the perfect box. Think about what happens when a curving line rises, hits a peak, and then drops back down into a valley. Those peaks and valleys, those are our critical turnaround points. At the exact top of that hill, or the very bottom of that valley, the slope of the line is perfectly flat. It's exactly 0. And because the derivative gives us the exact mathematical slope, finding the precise spot where the derivative equals 0 is literally how we hack reality to find absolute local maximums and minimums. Let's actually optimize a real physical object, an open-topped cardboard box. Let's say we want to find the exact dimensions that give us a specific fixed volume while using the absolute least amount of cardboard surface area. By deciding to give the box a perfectly square bottom, our fixed volume constraint simplifies perfectly. It's just the base side x squared multiplied by the height, h. Next up, we write out the equation for the thing we actually want to minimize, the surface area. The surface area is that square base, x squared, plus the 4 rectangular sides, which is 4 times x times h. Now, using our volume constraint from before, we can substitute h out of the equation entirely, just boom, getting rid of an annoying variable. Now, following our optimization strategy, we just take the derivative of this brand new surface area equation, set it perfectly to 0, and solve. And when you solve that equation and find that single, solitary turnaround point where the derivative is exactly 0, that is a true eureka moment. You've just calculated exactly how to build the most cost-effective, perfectly structured box in reality using the absolute least amount of material possible. How cool is that? And honestly, that is exactly how we use the calculus physics engine. By understanding the fundamental difference between speed and velocity, utilizing similar triangles to set dynamic equations in motion with respect to time, and setting derivatives to 0 to pinpoint absolute minimums, you can literally read the secret code of the physical world. So I'm going to leave you with this thought. If calculus really is the engine coding our reality, as you walk outside today, what other hidden rates of change are happening around you right now? Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.